My name is Sven Efftinge. I work for a consulting company called Eclipse, and we help people developing languages, tools, do modeling stuff and projects more or less throughout the world, but we are based in Germany, Switzerland, and France. We are also developing some frameworks at Eclipse. One is Xtext, which has already been shown by Ed a bit. We also have developed a new language, an alternative to Java called Xtend, and which is developed in Xtext. And in this presentation, I want to show you how you can implement a language with Xtext. So what does it feel like to build something like, for instance, Xcore? Who has tried Xtext so far? Okay, very good. So it's a language framework, which means you can develop programming languages with it as well as domain-specific languages. Domain-specific languages are more or less programming languages, so they are executable, but they are much more simpler usually. And you would not only implement a language, which is developing a parser or something, or a compiler, but you would also implement an IDE, an Eclipse plugin for that language. And so that's the idea, to have a very concise way to express what your language looks like, and from this definition you not only get a parser, but you get everything you need in a working language infrastructure, which is parser, linker, compiler, interpreters, and the IDE. Xtext is used by many big companies, small companies around the world, in research projects, in products. For instance, IBM used Xtext in one of their commercial products, and they actually switched over to Xtext in that product because before that they used on their own language framework, but they switched to Xtext, which is quite interesting. Okay, so let's have an example to learn how to build a language with Xtext. I guess most of you know who Martin Fowler is. He wrote a book about domain-specific languages, and in that book he uses an example to show how to implement a DSL in various technologies. So the example goes like this. Imagine you're working for a company which creates or specializes for secret compartments. You know, these special hidden panels or hidden rooms in old houses, which you know from movies. And you have one customer, which is Mrs. H, and she wants to have such a panel in her bedroom. And you're the consultant, and you discuss what the mechanism would be like for her. And she wants it to only open after she has closed the door in her bedroom, opens a second drawer in her chest, then turn the bed light on. And only then the secret panel should be open. Okay? So that's the idea. And you have hundreds of these customers, and everybody wants to have a different system. So you need a nice, concise notation to define these systems. So Martin Fowler came up with this language. So this is a definition of the system for Mrs. H. You first declare the events, then you say which of these events is a reset event. So you see on the top right there that if anybody opens the door, the whole system falls back into idle state. That's the idea of a reset event. And then on the left-hand side, you see there are commands. So a state machine needs to do some side effects in order to be useful. So if there's a transition from one state to another, you typically want to have some side effects. For instance, really closing the door, right? A mechanism. So you're sending a message to the lock, for instance. And then there are the states. So the first state is idle, and there you declare the actions. So whenever the machine goes into the state idle, the unlock door and the lock panel commands are executed. And then it's waiting for an event. So this notation with the arrow is a transition. So it waits for the door closed event. And when that happens, it goes into the state active. So that's the idea. Okay? Does that make sense? Not really? Oh. Or is that a yes? No. Let's see. Okay. So the idea is to implement these languages. And most people are pretty scared about even learning a new language. And implementing it sounds even scarier. So, yeah, people usually think, well, I don't want to implement yet another language or so. It's complicated. And the thing is, real programming languages, to implement them and to learn them, that might be a bit complicated. But a domain-specific language like this simple state machine, that's quite simple. So this is what Martin Fowler wrote up, which explains how to implement this language. So he explains the example, and he just explains how to build a lexer and a parser, and so you end up with an in-memory model of what was parsed. He calls this the semantic model. You can think of it as a DOM, right? If you have an XML parser, you give him some XML tags and you get a DOM. So this is what Martin Fowler calls semantic model. Usually it's called an abstract syntax tree. It doesn't matter. It's some model. In Xtext, it's an EMF model, what you get. So you see it's a lot of code here you have to do, and you will end up with just a parser, which is not so helpful. So the idea with Xtext is to simplify this dramatically. And we did so by defining a grammar language which allows you to just describe the language in the first place and a lot of aspects in it. And from this language, a lot of infrastructure is derived. Not only the parser, but also how the parser constructs an EMF model. Actually, the EMF eCore itself can be derived from this grammar you see on the left-hand side. And also this grammar is bidirectional, which means you not only can get a parser, but you also get a so-called unparser or serializer. That is, if you have an EMF model in memory and you do some changes on it, pass it to the serializer, and you will end up with a text again. So both ways work here. So let's see what happens here. A grammar is made of rules. And the first rule is called state machine. Then we have event, command, state, and transition. And it always starts with the first rule when it comes to parsing. And there we see it requires a keyword events. And you see it on the right-hand side. In the model, it's there. And after that, we want to declare events. And an event is just made of one name. So we call to another rule, the event rule, which is declared here. And therein it is defined that an event is just made of one identifier, ID. ID is a rule which you can reuse. It's like a Java identifier. That identifier is set into the attribute, the EMF attribute name of the event object. And then this rule returns an event object to the state machine rule, and this event object is added to the events property. So that's how the parser creates this EMF model while parsing. The next section, the reset events, is an optional part denoted by the question mark. And then you see the square brackets here. That's a special notation for cross-reference. So the events in the first section will be contained in the state machine. It's a containment relationship. So this is the actual declaration of events. And the reset events, but are just a cross-reference to previously declared events. So that's a big difference. And it also You can show it in, see it in the tool. So this event will be a cross-reference. So you get content assist to existing events. You get find references and rename refactoring and all these things. So then we have a command section, and after that, we have states. States also have keywords and name and an optional actions part, and then some transitions. And a transition is made of a cross-reference to a declared event, followed by an arrow, and a cross-reference to a declared state. So this grammar is all you need in order to have a full implementation of Martin Fowler's example. And let's see what it looks like in action. So this is a model in the generated editor. You see it has some coloring here. It has, of course, like these commands and comments are put in by default. You have these cross-references, as I said, really result in real cross-reference, content assist, statically typed. So you have go to declaration, you have find references here, and also here, all these things are cross-references. So you end up with a statically typed language. If you misspell something, like for instance here, you immediately get feedback, right? Okay, so, and we also have like rename refactoring. So I can, like for instance here, rename the turn the light on event. This would work cross-file in the whole workspace, like in Java. We only have one file here, but usually this linking works in the workspace. That is, Xtext has an index, which works generically for all Xtext-based languages. And you can even have a look by pressing Command Shift F3, which opened the Open Model Element dialog, which is similar to Open Type dialog in JDT. And then you can type some name, and you see all the elements which with this name, and you can open, and it will open the correct model automatically. So all these things come for free, just having the grammar in place. Oops, what's this? But in order to do something useful with a model, you want to have it executable somehow. So there are two ways to make a model executable. One is to translate it to another language which is already executable, like Java, which is usually referred to as code generation, or you have an interpreter for that language. So both ways are possible with Xtext. I chose to have a code generator to Java in this place, and this is of course not derived from the grammar because these informations are obviously missing. So what I had to do is, so this is my workspace where I developed the language. This is the grammar, and this is the code generator. And I don't want to go into detail here. You just see it's one class, and it is a mixture of a model transformation. So you turn your state machine elements into Java classes and methods and fields and so. And as soon as you want to have some behavior in the method, then you do text-based code generation. So then you can do Java code generation. That's how it works. And then you end up with this Java class here, which is executable. So I put in a main method. Let's execute it. So this is a command line based state machine. And it says we are now in state idle, and the possible next event would be door close. So let's fire that event. Now it's in state active. I have to turn the light on. and now I unlock the panel. Okay, so a very simple way to translate the state machine to something which is executable. Okay, so all this stuff is basic Xtext, which has been available for some time. And we've been working on some new stuff. And Ed already showed something of it, which is an expression library called XBase you can reuse in your grammar very easily. So whenever you do this kind of modeling and you have these models, the thing is, doing the structural stuff is very, very simple. It's really, really easy to define this structural coarse-grained things. But as soon as you want to have some behavior, some expressions in it, then really things become complicated. And that's why all these languages don't support this. So the commands here are just a declaration of a command, an abstract declaration, but a real command should express what it does, the side effects it does. I want to call some service, I want to call the lock mechanism of the door within the command. But how do I do in this language? I can't. So what people usually do is they go to the generated code and generate it such that it's easy to extend it. So I have, for instance, generated a method for each command and just printed the system out println stuff here. And if I want to have real behavior, I would go and change the generated code. I would use some subclass and override this stuff, some way of integrating it. All these things are actually workarounds. Because what you really want to do is you want to express it here. You want to write like, upsala, ciao Firenze. Okay? And then you want to have this executed. So let's see if that works. Ciao Firenze. So you might not want to have very complex logic in your model. That's not the idea. But I also don't want to have very complex model in this generated code here. I want to refer to some service. I want to call some service or have like 2 or 3 method calls within. But I want to be able to have that in my model, not elsewhere, and having some generated code, tweaking mechanism, and so on. So that's the idea. And it goes so far that you can really do very advanced things like, one thing I want to mention is this expression lives in the scope of this method, which means that there is this, and I can call, for instance, all stuff which is defined on the generated class. Okay, so you would, if you want to have local variables, you would generate a Java method with parameters, for instance, and pass them in, and then they are accessible in the expression without having them here in the model. So I can do very advanced things like A, B, C, and I can override. And let's print. So this is really a Java lang string. I can call everything which is defined on string here. And it links to it. It would be refactored. If I refactor that method, I'm not able to refactor to uppercase in Java lang string. But that all would work. And what I can also do is I can debug it. So I can put a breakpoint into my model. And if I try to open the panel, draw open, light on. I'm in debug mode now. And you see, I am stepping through my model. But it's really the Java debugger, so I can step into, and I'm now in the Java again. Step over, you see it on the console, the A. And I can even switch here to see the Java code, the generated Java code, and switch through that. So this is really a very tight integration of your modeling and your Java project. That's the idea. There shouldn't be any bad turnarounds or gaps between that. Your model should just be a very nice way to express certain aspects of your software system. And most of your software system should still be, it usually is Java or when you are in a Java project. But then there are certain aspects, like state machine or so, you want to express it with this. And that's the idea. So that's all I want to show today, and I think my time is up. So do you have any questions? Maybe one question? Yes?
Suppose that we have an expression language that is mostly Java. For example, I have to do something like new array and so on. And I saw that space doesn't support the static method call. For example, you have to use the point. There is no Java. There is the Java syntax. Isn't the same in space, right?
Okay, so the question was, the comment is that Xspace is not exactly the same syntax as Java.
Yes.
That's true. There's, for one thing, we removed a lot of boilerplate, so you don't have to express types over and over again because there is a type inference engine, and so it's more like maybe Scala without the complex type system. And then there are some situations like you mentioned this call to static methods.
Also array, for example, the array initialization is supported in space in the same way that is.
Yeah, so we made some differences. Yeah, in some scenarios we clean up the syntax. We also removed old stuff from Java, like there is no old style switch, for instance. The switch in Xspace is much more powerful. And you also mentioned array access, which is something we are currently working on it. So, but you can do most of what is possible in Java in Xspace already.
But suppose that I need to write my expression language that use a Java like syntax. So I have to write array and use a static method call. Would you suggest for the moment to write my own grammar or to reuse the Xspace grammar and maybe extend it?
I would suggest to rethink whether it really needs or why it really needs to be exact like Java. So that would be the at least painful way.
A Java-like grammar plus other stuff. So
Yeah, it's Java-like. I think Xspace is Java-like, but there are subtle differences, yeah.
yeah, I know. But we need to write Java plus other stuff. Maybe I can show you later what I mean.
Yeah. So it will be, it's not so simple to make Xspace being a real subset syntactic-wise of Java.
Okay.
So,
There is also a way to rewrite some of the rules of Xspace.
yeah, you can extend Xspace, you can introduce new literals or whatsoever. That's quite possible. But for instance, introducing arrays, you would have a conflict with lambda expressions as we have them in Xspace, which use the square brackets, like in Smalltalk. And the square brackets would conflict with the array access in Java. So you would have to disable certain features in Xspace in order to use them elsewhere. Okay. Thank you.